Right, this is the last lesson that we're going to cover. Uh-oh, how do you do this? All right, there you go. This is the last lesson we're going to cover. So what I hope is going to happen is we're going to get it covered today. I'm not sure if we're going to get it all covered. And then the second part is we'll have Monday to work on it. Hopefully Tuesday you'll have a quiz on 1516. Get the review for the benchmark. And then the benchmark will be scheduled for Friday of next week. The only thing that's the downplay on that is how many are taking, I think, is it the ASVAB on Tuesday or PSAT on Tuesday? Is there anybody doing that? Okay, well, if we're not sure about that, that's the only thing I might play and push things back. Because if we're going to have a lot of kids out, then I'm probably going to push some stuff back. The next thing I want to make sure that you're all aware of is I just lost my train of thought. I don't know what it was, so we're just going to get started on this. But anyway, so let's get started. We're going to talk about inverse functions. This is the last piece of the puzzle. Inverse functions are when you basically switch your x and y and solve for a new y. And you get a new function, hopefully. A lot of times, every equation has an inverse. Every relation has an inverse. The question is it a function? Is it an inverse function? And so we're going to kind of go through this. And we're going to kind of recognize what we have here. So if we look at this right down here, it says, for instance, we have the function f of x is equal to x plus 4. And I say, hey, I want this set domain. I want to look at x equals 1, x equals 2, x equals 3, x equals 4. Well, I get that outcome by plugging those values into that expression or that equation. And so I basically get, hey, when x is 1, y is 5. When x is 2, y is 6. When x is 3, y is 7. And when x is 4, y is 8. And you can write those as ordered pairs, which hopefully we already know that we can do that. Now, when we reverse that, then I could say, hey, if I reverse it, then I say the 8, the 7, the 6, the 5 become the new set A. And then the 1, 2, 3, and 4, they come the new set B. That's what an inverse is. It just switches up your x's and your y's. So when we look at that, that's exactly what this is saying down here. That you just interchange. They just switch up. So the inverse would be 5, 1, 6, 2, 7, 3, 8, 4. Does that make sense? They just switch. That's all they do is the order pairs switch. The next thing is, the most important thing, is that the domain of the first function becomes the range of your inverse. And take that, yeah. And then that's right. And then the range of your function becomes the domain of your inverse. So the domain of the original becomes your y values. The range of your first function becomes your domain, the x value. So they just switch. X and y switch. X and y switch. If you don't hear anything else here, x and y switch. Questions on that? Good? Okay. And so now here's probably the most important piece. We're just going to talk through some of this and then we'll run through it. If you see the words, very, 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 very important. If you see the words verify, show that these are inverses, there is a process. You have to plug the inverse into the function and the function into the inverse and show that they both come out to be x. That's what you have to do. And we're going to do this enough that you're going to see it in a minute. But that's what we're going to do. If they are truly inverses, then they will, when you plug one into the other, you will get x. And so basically that's kind of telling you, hey, this will be symmetric to the line y equals x. And we're going to see that in just a minute as well. So here we are. It says find the inverse. So we're finally down to the first example. Find the inverse. So what have you heard me say so far? To find the inverse, you do what? Right. So first I'm going to first make this just y equals 4x. So it's a little bit easier to deal with instead of having function notation. So when I do that, I'm going to switch them. I'm going to say, okay, well, we got x equals 4y. Now what do? You solve for the new y. You solve for y. You make y get by itself. Make it say y equals. And so you're going to divide both sides by what? 4. So your inverse is going to be x over 4. And again, inverse notation is f negative 1 of x. So we take f and then we raise it to the power of negative 1 of x. And so we can say that's x over 4. Does that make sense? Now I want to verify. Prove to me that these are inverses. So I'm going to go do this composition function. And I'm going to write it both ways just so that you're aware that you can see it. So we're going to write it both ways because it means that, hey, I could look at this either way. They could be written the same. And so this says you're going to take your inverse and plug it into your function. You're going to take your inverse and plug it into your function. Well, this is your inverse. This is your function. You're going to plug this into here. So you're going to get 4 over x over 4. So this is really going to become important of your order of operations. You have to know what happens first. PEMDAS, please excuse my dear Aunt Sally, however you remember it. And so what happens? Well, you're going to get 4x over 4, and that reduces to x. Check. Not good enough. Not good enough. You have to do it the other way as well. Now you have to take your inverse and substitute in the original function. Okay, and again, that notation is f negative 1 of f of x. Okay, that f negative 1 of f of x. And so I have to take the function 4x and plug it into this guy. Well, when I do that, you're going to get 4x over 4. And so what does that reduce to? X. I'm going to tell you now, this question's on the test. It's the biggest point value on the test. And a lot of kids, they blow past this on the homework. They don't practice it enough. And so therefore, lots of people miss it on the test. I'm just going to tell you that, right? And you're going to be asked to do it 100 times. Questions on that? Everybody good? That's verify. Show that.
You always do it both ways?
Both ways, always. Always both ways, yes.
Does it matter which one we do first?
Nope. Nope. And it should always come out to be x. If they say they're inverse and they say verify, verify means, hey, this is true. I mean, this will be true, so it better come out to be x. Got it? Okay. And the other thing I need to be able to do is I need to be able to see your math. And again, we're just defining inverse functions. If you have inverse functions, whether it's g of x and f of x, and they say they're inverses, again, you have to comply that composite function. And again, it answers the question, you have to do it both ways. You have to show both. Good? Now, the other thing that is very important about inverse functions, again, it all goes back to switch x and y, domain and range change. And so you just got to keep that in your head. As long as you keep that in your head, I think it's pretty easy to do. So when you look at this and you have a function, if you have a point a, b that is on f of x, and then you have the inverse function, well, then that point's going to switch. You see how they switch? The a became the y, and the b became the x. Make sense? Good? All right. So we should be okay with that. And it should all be symmetric to the line y equals x. So in other words, if I fold that along y equals x, everything's going to match up perfectly. Kind of looks weird because sometimes they overlap, and that's okay if they overlap. Okay, moving on. So here it says verify the functions g and f and g are inverses of each other graphically. So we want to graph it. So if you didn't get a graphing calculator, we're going to have a little bit of chaos here. Let's get a graphing calculator. If you didn't bring one in or didn't get one, grab one out. So I'm going to show this a little bit. I'm going to cover some stuff up, but we're going to graph them. And so the very first thing you're going to do is you're going to graph in the f of x. So make sure, again, you're at y equals. When you go to graph, remember you hit zoom 6 to get it back to a standard window. Negative 10 to 10, negative 10 to 10. So we type that in, 2x to the third minus 1. And then we type in the cube root. Cube root, we may not know where it is. And so that's a function I need to make sure that I share with you. So to get to this cube root, you're going to go hit math. But before you do that, you're going to hit 3 because you want to recognize this. No, I don't. Never mind. You don't need to do that. So you're going to go to math, and you're going to go down, and you should see it, number 4. So it's at math, number 4. And then again, how are we going to type that in? It's going to have to be in parentheses so that you know it's order of operations. X plus 1, close up your parenthesis, divide by 2. And again, you can't see that very well, but hopefully you're ask somebody next to you if you've lost track. And then you graph. Here comes the first equation. Here comes the inverse. And so it looks weird, but they're saying, hey, if you fold that along the line y equals x, you're going to have every point match up with a point on the inverse. Now, the other way you can double check that is go into y equals and hit y equals x, because that's the line it's supposed to be able to be folded along. And so when you hit it, I think it does give you a nice picture that says, oh yeah, they do match up pretty nicely. Good? Can't see that very well. Now, the other way you can go back and look at this is look at your table. And let's go to your table where it looks nice. We're going to start at maybe 0. No, we'll start at -1 or -5. And then go up by 1. And go to your table and notice the numbers are just going to switch. Like I'm going to pick a point, -1, 3. Then it's going to be what? -3, 1. Do you see it? The x's and y's will be there. They'll switch each other. Do I need to go back through something? Do which part again? The table, all of it?
Yeah.
Okay, so we're going to go y equals, right? We got those in there. It's 2x cubed minus 1. And then the cube root of, in parentheses, x plus 1 divided by 2. Good. And then in the third equation, I've got the y equals x. If you want stuff to graph again, you just got to kind of re-enter something. So again, here comes the first equation. Here comes the second equation that you put in. And those of you that have nice color, you got nice little divisions because everything's color-coded and it looks really pretty. And then here comes your y equals x. And again, you can look at that and say, hey, if I fold here, it'll match up with this one. If I fold here, it'll match up with this one. And so they'll be the same point. They'll just be reversed. Does that make sense? And so then when you go into table, which is where I think I lost some of you. When you go into your table, you're going to look at that and you're going to say, first of all, mine was all messed up. So just as a reminder, you're going to hit second window to get to your table set. And I wanted to start my table at -5. And then I did my change in table as 1. So that way my table will be -5, -4, -3, -2, so forth and so on. Does that make sense? And so then I'm going to go to the table. And that's where I'm going to try to show you real quickly. It's hard to see, but on yours, hopefully you'll see it. I took the point and I got, hey, -1, -3. Well, then when I go look at the second graph, you're going to come up here and say, hey, well, here it became this. -3 became the x, -3, and on the second equation, my y was the -1. Does that make sense? So they just switched. There's going to be a switch for every single one in there. So when you look at the two different equations. And so that shows it graphically. Now, does that make sense? But when you see verify, what does that mean you need to do? More importantly to me. You plug them in to each other, correct? So let's do that by hand. So we're going to take f of g of x. That's that composite function we just did yesterday, right? That was 1.5 knowledge. So wherever I see a cube, this is what gets hard. Wherever I see a cube, this entire thing goes. So I'm going to go 2, and then here we come. Big O cube root. X plus 1 divided by 2. Close that up, minus 1. Now, this comes straight out of order of operations. So, and we got to cube that, right? Sorry, I forgot my cube. So we have to kind of know how things undo. They're going to just undo themselves. They're just going to unwrap. Now, here's the important part. This is the part I need to see. You can't just get all mark out happy. I have to see the logic. I have to see that you know order of operations. So it's a process, but it's an easy process. What will the first thing happen? What will go away first? Cube root in the cube. And so I'll be left with 2 times the quantity, x plus 1 over 2 minus 1. Now what will go away? The 2's. X plus 1 minus 1. What will I be left with? X. Right? So I have to just show that I'm going to take away one thing at a time, correct? One thing is going to disappear because you have the reciprocal or an opposite involved. Now we have to go do it the other way. So I'm going to squeeze over here, and everybody have that one? Because I'm going to go over, and I think we're going to lose it. But now we have to go the other way. We have to do g of f of x. And so again, I'm going to have to drop down because I'm afraid you're not going to be able to see it very well. So we're going to take the cube root. And wherever I see the x, I have to put that whole f of x. And so I start my cube root. Oh, there's x first right off the bat. So I'm going to have to go 2x cubed minus 1 plus 1 over 2. Now, again, I have to be able to tell what order of operations. So when I look at that, what will be the first thing that goes away? Minus 1 plus 1. So I will have cube root of 2x cubed over 2. What's the next thing that will go away? The 2's will divide out. And then when I take the cube root of x cubed, what will I get? X. Check. So again, that's probably the more difficult piece. And I'm here to tell you that it's on the quiz, it's on the test, it's the most points, and you have to verify. Verify, show that algebraically this is the process. What we have a lot of kids do is they just they switch the x and y on one and show that, oh yeah, it came out to be that inverse. It's right. That's not verify. That's not show. Right? That's finding. And then you're not validating it. Correct? Questions on that? All right, I am going to skip example 5. I would highly encourage you to play with it if you can. It's just trying to show you how you can graph the inverse from the original function. Those of you that are kind of computer nerds, you might like that, or graphing calculator nerds. Hopefully there's some people in there that are like that you can figure that out. So due to time purpose, we're just going to skip right on over that. The next thing I'm just going to emphasize that the next thing I'm going to emphasize is that you have f of x is equal to x minus 5 over 2 and g of x is equal to 2x plus 5. If I'm telling you, hey, these are inverses of each other, then what's going to happen? Again, I'm emphasizing that they change. So on the first one, x is negative 2. You got your outcome to be negative 3.5. Well, then if you plug in negative 3.5 into g of x, guess what you're going to get? Negative 2. Again, it's just showing the what? X and Y's what? Switch. That's what it is. The points they're just going to switch them, and then you get your graph of your inverse, correct? So I can graph an inverse quickly graph an inverse if I have points on my regular graph by just switching them, correct? And then graphing the new one. I don't have to find it. So a lot of times in your homework, they're going to ask you to graph the inverse. So very, very important. They're going to tell you to graph the inverse, and they're going to give you the graph of the function. Well, they're doing that because finding the inverse is a little bit more difficult to do. So they just want you to switch your x and y's and plot the new graph. Does that make sense? Switch your x's, y's, and plot the new graph. Okay. So the next thing is, how can you tell if an inverse is 1-to-1? How can you tell if an inverse is 1-to-1? Well, this is probably the most specific thing. That's saying that you get a function. That's saying that, hey, when I take my x and y and I switch it and I solve it, then I'm going to get another function. So that means it's 1-to-1, just like if you learn back in geometry, if and only if statements. And that's saying, hey, it's a one-way street either way. Like there's not multiples. I can't jump and have more than one y or more than one x at any given time. 1-to-1, exactly what it means. One x for every y and one y for every x. Got it? Okay. So the other way you can do that is if the original function passes a horizontal line test, you will be able to tell that it is a 1-to-1 relationship. So we know that we can pass a vertical line test here and say, yep, that's a function. But the question is the inverse a function? Is the inverse a function? And you say, well, you know what? Let's do a horizontal line test. And if, again, just like a vertical, if it only hits the horizontal line in one spot only, then yes, the inverse is going to be a function. So is this going to have the inverse going to be a function? No. Inverse is not a function. And again, if you think about it, I'm going to kind of go back to those parent graphs, but we're not in my room. X cubed and a cube root. Those are inverse functions of each other. X cubed and a cube root. And then you have the quadratic and you have the square root. Well, you have to fix domains and range if you want those to be inverses of each other. You have to just look at part of it, because a quadratic and a square root, they are not going to be inverses. This is the quadratic, and the square root would look kind of like this, right? But it would really look like this if it was the inverse. Does that make sense? And so it's not going to be, they're not really inverses of each other. But a cube root and a cube are. So the next thing that is kind of special is if you have two different graphs that are either decreasing or increasing all the time. Well, basically, what's that? That's really a linear function. That's really your y equals mx plus b. They're always going to be 1-to-1. So basically, when you switch your x and y, you're going to get another line. A cube and a cube root. Those are inverse functions of each other. Because they're either always increasing or always decreasing. They're always going up or they're always going down. Does that make sense? Next, we're going to skip over example 7. Actually, I'm just going to have you put a big old X into that. I'm not going to worry about that at this time. So, here's the moral of the story. We're going to recap and make sure. To find inverses, you have a graph. The original has to pass a horizontal line test in order for the inverse to be 1-to-1 and be a function. You can always find an inverse by switching x and y. To verify them, you always have to plug them into each other both times and show that it comes out to be x. Good? And so it kind of gives you that description. So now here we are, find the inverse function. And I want to just kind of address this a couple ways because a lot of kids have issues with this. This is 5 minus 3x over 2, which, mind you, is just a line. But a lot of kids won't see this as a line. It's a line because I could write this as 5 halves minus 3 halves x. So I might have to think, which way is better? Which way do I want to look at this at? What's going to make my life easy? Right? That's what you want to do. But remember, I don't really care if you simplify it, what way you simplify it. Either answer is fine. But anyway, we're going to find the inverse to this. So how do you find the inverse? You switch the x and y. So we're going to just say this would be x then equals 5 minus 3y over 2. So we want to find it. Now again, the situation is that you have a whole number equals a fraction. So we cross multiply that. And so when you cross multiply that, that will give you 2x equals 5 minus 3y. And then what will we do? We're solving for y to get the inverse. We wanted to say y equals. As soon as you make that switch, you make it say y equals. And so what do you do now? Subtract the 5. And then you'll do what? Divide by negative 3. Everything by negative 3. Can you write this as dividing everything by negative 3? Yes, or can you split it up as well? So can you do 2x divide by negative 3 minus 5 divide by negative 3? Yes, either way is fine. Both are okay, right? I don't care. So what's the inverse at the end of the day? Y equals 2x minus 5 over what? Negative 3. Now, I will tell you, in the back of the book, they will do something that's called give me the least amount of negatives. Because really in the math world, you want to have the least amount of negatives as an answer. So when I look at this, you're going to get y equals a negative 2/3 x plus 5/3. That's an option. Or it could be negative 2x plus 5 over what? 3. They're going to simplify that negative every single time. Does that make sense? Because they don't want, if they can get down to one negative or the least amount of negatives, that's what's going to be. And so I have a lot of kids when they start looking in the back of the book, they're saying, well, this is different. Are they the same thing? Many times, yes. Right? Many times, yes. Yes.
So on like a test or a skill check, if we did, like, if we just had the original answer where it was 2x minus 5 divided by negative 3, would that still be counted as correct?
Good question. I'm going to repeat that just so these other classes can hear that. If you gave me the original 2x minus 5 over negative 3, would I count that on a test? Yes. Yes, I would count that on a test, right? So if it was a multiple choice, though, you might recognize that it could be written as one of these other ways. Correct? Okay, good. Here we are, verify. Again, whenever you see the words verify and what? Whenever you see the words verify, or what's the other word I said? Show that, right? Whenever you see verify, show that. It says, you have to show me that it's going to be an inverse. We probably will even emphasize the fact and write that. Show that you're going to get x. You plug the inverse into the function into the inverse. So when we do that, you're going to get f of -1 of x. Again, you get 5 minus, and then I see the x, and so in comes the inverse. 5 minus 3, 5 minus 2x over 3, and then all over what? 2. So again, that can be confusing, but you just got to make sure you take your time. Wherever you see an x, you got to plug in that entire function. Again, now this becomes order of operations. You can't get, if you just start marking stuff out, I'm not even going to waste my time. I'm just going to do -4. So you've got to make sure you show me how the math goes away, how it dissolves. So what's the first thing that will go away? The 3's. And I'll be left with 5 minus 2x all over 2. And then what will I have to do? And again, I'm not marking stuff out just simply because you can see the thought process, correct? All right, then what will happen? Well, you'll have to distribute that. And so you'll be left with 5 minus 5 plus 2x over 2. Now what will go away? The 5's, and then what will you be left with, which I've ran out of space? X, check. Good. So again, that's really going to push your order of operation knowledge. And some of you may think, hey, I want to distribute this 3. That's okay. You can distribute that -3 and then divide each piece by 3. That works too. Now we got to do the other way. So now we're going to take the inverse and we're going to substitute in the original function. And so we do that. We're going to get 5 minus 2. Here comes the x. So here comes the function. 5 minus 3x over 2 all over 3. Correct? So again, once you do these, the problem is you got to practice them because I can't tell you that they're going to all look like what's on the examples. So you've got to just make sure you do all kinds. So what's the first thing that's going to go away? The 2's. Then what are you going to do? Distribute. Then what's going to go away? The 5's. What will you be left? What will you be left with? X, check. I got to see the math and I got to see the thought process. Good? Okay. Find the inverse function. So we're going to stop right here, or not stop. We're going to finish this one, and then I think we might have to stop. I think we're done after that, so we're going to get through this, I hope. All right, so here you go. Find the inverse. How do you find the inverse? Switch x and y. So we're going to get x equals the square root of 2y minus 3. Now what do you do once you switch your x and y? Solve for y. So how you make it say y equals. And so what's the next thing we have to do? Square both sides. Then what will we do? Add 3. And I'm just going to rewrite it up here so we can see the thought process again. And then what will we do? Divide everything by what? So this would be an answer if you chose x squared plus 3y over 2 equals y, or what's the other way I could write it? 1/2 x squared. I lied. There's not a y somewhere. Where did I get my y? That's an extra y somewhere, didn't I? Sorry, so sorry. And then 3 over what? 2 equals y. Both of those answers are acceptable. Good? Okay. I think I am going to stop here because we get out here at 8:42. And I'll finish this last one up. You can try it, but it has a fixed domain. And so we'll have a fixed range so that we can get an inverse function out of the deal. Correct? And so we'll talk about that in just Monday when we first get back. So what I suggest you to do is try some of this homework just in case you're one of those people that are going to be out on Tuesday, because I do believe there's some people testing on Tuesday. Is that not right? Yeah. So if that's not you, then you might miss that work day. So you might want to get ahead of yourself so that you're good to go, or that quiz, and we'll get it all lined up definitely Monday what's happening. Yeah, it's always great.